Imagine a jet engine pushing its absolute limits. At 1400 degrees Celsius, even the most advanced high-performance steels begin to behave like warm butter, slowly stretching until they inevitably fail. But there is a new material emerging from the labs of Virginia Tech and Johns Hopkins that flips this script. It doesn't just survive the heat, it thrives in it, becoming tougher as the environment becomes more extreme. This is the unbreakable MPEA, a multi-principal element alloy that marks the biggest leap in metallurgy since the Bronze Age. And the secret to its power lies in a beautiful, chaotic atomic mess. For thousands of years, humanity has followed a simple recipe for metal. Pick one host element, like iron, and add a tiny pinch of something else to change its properties. We call this microalloying. But this approach has a ceiling. When you push these traditional metals to their thermal limits, the atoms start to slide past each other. This is creep, the slow, silent killer of every machine we've ever built. Engineers have spent decades trying to stop this sliding. They've tried coatings, cooling channels, and complex crystal growth. But the solution wasn't to fix the old recipe, it was to throw it away entirely. On March 24, 2026, researchers from Virginia Tech and Johns Hopkins announced they had finally cracked the code for a stable, high-performance MPEA. They didn't just make a new metal, they engineered a new state of matter. This alloy is what material scientists call entropy-stabilized. By mixing 5 or more elements in nearly equal proportions, they created a lattice so complex that it refuses to break down under pressure. It sounds like a paradox, using chaos to create stability. But in the world of mechanical engineering, this cocktail effect is the key to unlocking properties we once thought were physically impossible. The unbreakable claim isn't just marketing hype. In testing, this alloy showed a fracture toughness that actually increases as the temperature drops toward cryogenic levels, while staying rock solid at the melting point of most other metals. This means we can finally build engines that are lighter, hotter, and significantly more efficient. It's the difference between a machine that wears out and one that lasts for generations. But to understand why it works, we have to zoom in past the surface and look at the atomic architecture that makes this metal a mechanical masterpiece. The hidden complexity here is staggering. In a normal metal, if an atom is out of place, it creates a weak point. In an MPEA, every atom is technically out of place because they are all different sizes. This lattice distortion is actually a feature, not a bug. It creates a bumpy atomic landscape that acts like a series of speed bumps, stopping cracks before they can even start. The engineering required to balance these 5 elements perfectly is what we're diving into next. Because mixing them is easy, but making them stay together, that's where the real genius happens. To understand the MPEA, think of a standard alloy like a bowl of white rice with a few peas mixed in. It's mostly one thing. But an MPEA is like a perfectly balanced 5-bean chili. In this cocktail, no single element is the boss. Chromium, cobalt, iron, manganese, and nickel all have to share the same crystal lattice. This is the multi-principal element concept. When you have this many elements in equal parts, something strange happens to the physics of the metal. The system enters a state of high configurational entropy. Entropy is usually associated with disorder and decay, but here, the massive amount of disorder actually stabilizes the crystal. It's called entropy-stabilization. Think of it like a crowded elevator. If everyone is the same size, it's easy for people to move around. But if everyone is a different shape and size, everyone gets wedged into place. Nobody can move. This jamming at the atomic level is what gives the MPEA its incredible strength. The atoms are so busy trying to fit around each other that they simply refuse to slide, even under massive loads. Now, here is the really counterintuitive part. In most metals, heat is the enemy. It makes atoms vibrate faster, making it easier for them to slip and for the metal to soften. But in the Virginia Tech MPEA, heat actually helps. As the temperature rises, the entropy effect gets stronger. The disorder that holds the lattice together becomes more dominant, effectively locking the metal in place. This means the alloy has a negative temperature coefficient for certain types of deformation. It is one of the few materials in the world that can actually become more resistant to certain stresses as it gets hotter. This leads us to the engineering holy grail, creep resistance. Creep is what happens when a metal is under constant stress at high heat for a long time, like a turbine blade spinning for 10,000 hours. In the MPEA, the speed bumps we talked about earlier, those different-sized atoms, are so effective that the atoms can't migrate. The creep simply doesn't happen at the same scale as traditional superalloys. By stopping this atomic migration, engineers can push engines to higher pressures and temperatures than ever before, extracting more energy from every drop of fuel. But there's a catch. To get these properties, the atoms have to be perfectly distributed. If they clump together, a process called segregation, the whole thing falls apart. The Virginia Keck team solved this by using a specific cooling rate and mechanical alloying techniques that force the elements to stay mixed, even when their chemistry tells them to separate. This is the cocktail in its final form, a perfectly frozen explosion of 5 different elements working together to do what no single metal could ever achieve alone. If MPEAs are so great, why isn't everything made of them? The answer is a manufacturing nightmare. Most of these elements actually hate being near each other. It's like trying to mix oil and water, but with 5 different liquids that all have different melting points. If you're not careful, the manganese will boil away before the nickel even melts. Maintaining a single-phase solution where everything is perfectly blended at the atomic level requires a level of precision that pushes current industrial hardware to its breaking point. To solve this, the Johns Hopkins team developed a millimeter precision quality control system. They use high-speed X-ray diffraction to watch the atoms arrange themselves in real time as the metal cools. If even a tiny cluster of atoms starts to group together, the system adjusts the cooling lasers in milliseconds to break them up. It's like a high-stakes game of Tetris played at the speed of light. This level of control allows us to manufacture parts with 0 internal defects, making the unbreakable claim a reality even for massive industrial components. The implications of this technology reach far beyond jet engines. In the freezing vacuum of space, traditional metals become brittle and shatter like glass, but the MPEA actually gets tougher. This makes it the perfect material for the next generation of deep space explorers and lunar habitats. It's a metal that can survive the transition from the sun-scorched side of a station to the absolute zero of the shadows. We are looking at a future where our machines are no longer limited by the materials we have, but only by our imagination. The Bronze Age and the Iron Age are over. We are entering the Entropy Age. Down on Earth, this alloy could revolutionize renewable energy. Geothermal power plants currently struggle with pipes that corrode and melt in the Earth's crust. MPEAs could last for decades in those same conditions. It could also mean safer nuclear reactors and more efficient hydrogen storage. By solving the material failure problem, we unlock the door to a truly sustainable high-tech civilization. The engineering behind this unbreakable alloy is a testament to what happens when we stop trying to fight the laws of physics and start using them in clever, unexpected ways. So, the next time you see a jet taking off or hear about a new mission to the stars, remember the hidden chaos happening inside its engines. It's not just metal, it's a perfectly tuned atomic symphony. The unbreakable MPEA isn't just a discovery, it's a promise. A promise that the machines we build today will still be working, stronger than ever for the world of tomorrow. And now that we've mastered the cocktail of entropy, there's no telling what other impossible materials are waiting to be mixed. The future is forged in chaos.